and plus bike lane. There's also an environmental.
Hey, I really appreciate that at least a couple of you, when I greet you in the morning, or now afternoon, I should say, that at least a couple of you sort of do unmute and say hello. So it allows me to know that indeed the audio is recording, picking up some volume. So how y'all doing?
Doing great. How are you?
Good. Doing okay. And a couple of you are saying, dude, just look in the lower left corner of Zoom because it shows the little microphone with the green thing waving. So indeed that you can know that you're being broadcast to somewhere. So I think we're good. But yeah, things are going well. I went to campus today for 15 minutes and it was brilliant and it was warm and the sun was shining. And I said, I need to get out of here because it's going to be hot. Okay, so hopefully your days go well. I think where we're at is halfway through chapter 7, confidence intervals. Yesterday, we sort of broached the topic of what is a confidence interval, how could we interpret one once it's calculated, okay? And today, I'd like to sort of present another confidence interval, sort of in the general class of confidence intervals that are large sample confidence intervals, the first one we hit. And then I'm going to sort of note that the one I'm going to present to you is actually pretty good for small samples as well, in the context of when this particular method can be used reasonably. And then I'm going to say, and so we should go back and talk about the other one we sort of introduced yesterday, a confidence interval for a mean. What if the sample isn't large in size? What can we do? What should we do? And we'll tweak the method a little bit and then close out today by saying, and if you want to estimate not just one population's mean, but rather the difference of two population means, literally how much higher is one group than the other on average, we're going to finish up there. I just noticed that the lab for today I have not yet put online. I apologize for that. I'm going to try and get that done ASAP after class is finished. And so office hours are right after this class, right at 1:10 till 1:35. And if no one's here for office hours, I'll get the lab done probably before 1:35. If there are people there for office hours, well, we'll chat. And then I'll sort of work on that thing right afterwards. So all should be good. Any questions about administrative issues before subject matter questions? Okay. How about any questions related to what a confidence interval is or anything we talked about yesterday when we derived a confidence interval? Okay, let me just then share a screen and we'll sort of dive into answering a question about yesterday's confidence interval, then move forward like I had suggested earlier. So here, nope, let me put this guy over here so I can at least see stuff that I need to or want to see. Okay, so yesterday we talked about this confidence interval, and let me remind you of the way that it looks. Our 100 times 1 minus alpha percent confidence interval for an unknown population mu, if n is big, we're allowed to use this particular method. And by big, I would say, 25, 30, 50 individuals will be a little bit more precise about what big is, but it depends on the nature of the population you're sampling from. But I'm just saying, hey, if your sample is large in size, we talked about estimating, again, thinking you want to estimate this unknown number mu, okay? And yesterday I talked about a 95% confidence interval, but in the lab you worked out that if alpha is say 0.05, the error rate is 0.05. Ultimately, this number ends up being 95%. So 95% corresponds with an error rate of 5% or alpha being 0.05. I could pick the alpha I want and get the confidence level that I want. And the confidence level is, if you will, the long run rate of success when you're using this method in an appropriate situation. The confidence interval is just going to be X bar, the sample mean, that's your estimator for mu, plus or minus Z, and I'm going to note that Z alpha over 2. So the upper tail area would be just alpha over 2. Your way of maybe thinking about that is just in the upper tail. Okay, you've got alpha over 2 up there, above Z alpha over 2. And so you tried in the lab yesterday identifying a couple different values for alpha and finding the corresponding level of confidence, and then the Z value itself. And plus or minus Z alpha over 2 times S over the root of N. That is our procedure. The overall margin of error, MO, is right there. It's the number following the plus or minus. And sometimes you want to say, I would like my margin of error to be fixed. I'll give you maybe a bound B. I want my margin of error to read no larger than plus or minus B. Plus or minus this number, I'd like to see that or even fewer. I guess I could use a little bit of algebra and solve then for B. If B is just Z alpha over 2 times S over root of N, and I want to know what is the sample size N that I'm going to need, the algebra tells me the N that I want should be at least the value. So you want the margin of error to be less than or equal to B. So the margin of error should be less than or equal to B. So N should be Z alpha over 2 times then S over that target margin of error B and square it. So you tell me you want to know the actual average length of catfish in the James River to within 1 millimeter. Plug in a 1 for B, solve for N. Just want to note one thing here. On the right-hand side, you do have a value S. That S is the standard deviation that you're going to get in the sample after you take the sample. And so some of you are correctly noting, hold on, I don't know S that I'm about to get in the future. Well, what we say is we plug in a good guess or sometimes a wild-ass guess. Essentially, you plug in a value for S that corresponds to the nature of the problem. If you've done a past sample of catfish in the James River and you know the standard deviation is about 190 millimeters, I plug in a 190 or plug in a value of S maybe a little bit larger than what you think is the true population standard deviation sigma, because that will cause the ultimate sample size you derive to be a little larger, causing your resulting margin of error to be less than B. But you should know the weak spot here is I don't know the S I'm going to get, so I might want to choose a conservative value for S. Pick a value of S that's maybe a little bit larger than that you think the population has as sigma. Any questions about finding a sample size? Okay, so I'd like to switch gears into a new method, and that is in the context of a binomial situation. If X follows a binomial distribution with N trials and pi is the rate of success, Okay, I would love to know pi. So my theta is pi, unknown. I guess lowercase Greek characters are typically these unknown values. I don't actually know the chance of heads with this. Well, let's go with this 1 Egyptian pound coin. Okay, I don't know the chance of heads with the coin. Probably close to 0.5, but I don't know what it is. Okay, and I would like to estimate it. My estimator, I'm going to call a p. Literally, I'm going to take the number of trials and divide through by then the number of, I'm sorry, the number of heads divided through by the number of trials. That's a sample proportion. Okay. Your expected value of your sample proportion. We could do the work, all that chapter earlier, and find that that's actually equal to pi. So maybe I would want to use pi. Maybe I'd want to use my sample proportion to estimate pi. We can also, though, use the normal approximation to the binomial, okay? Divide through by n and say that p is distributed approximately. So I'm going to write APP for approximately. Normal with mean pi. And you can use our earlier methods to find then the standard deviation of that. And the standard deviation is, so this is the SD. It's pi times 1 minus pi all over n. Okay? So if I tell you the normal curve, its central value and its spread, I could write the following. Okay, I'm sort of going to just algebra here. I could write 0.95, 95% is the probability that negative 1.96 is less than or equal to p minus pi. We're going to subtract off the mean, then divide through by the standard deviation, which is the root of pi times 1 minus pi all over n, and that's less than or equal to 1.96. Okay, from the normal curve, 1.96 magically yesterday corresponds to 95%. So I now have, and let's erase the part that's unclear and write it in more clearly. I've got here 1 pi times 1 minus pi in that parenthesis. Pi times 1 minus pi all over n, all within the root, including the n. So essentially, I guess this is a specific case of the general version that we could write out, and the general version is 1 minus alpha. Okay, is probability that z alpha over 2, the negative of that, is less than or equal to p minus pi all over the root of pi times 1 minus pi all over n, all again within the root. Sorry about that. Less than or equal to z alpha over 2. Okay, so I'm going to sort of go ahead and work the rest of the example as though you want 95% confidence. But in general, if you want a different level of confidence, the work you can do is going to follow from this equation with a different z value. Okay, so let's go ahead and dive in on that work. Let me just sort of note, if you multiply both sides in this equation, and I'm going to treat the left portion as though it's inequality, multiply both sides by that denominator, and then I guess we could work over here with that second part of the equation, okay? And again, multiply both sides by that denominator. I could write, I'm sorry, I could write this as, maybe I should go with red to continue the red from the earlier page. P minus pi, okay, should be, if I just plugged in inequality rather than the less than or equal to, I would write 1.96, okay, times the root of pi times 1 minus pi all over n. And again, we're trying to solve for n here. And let's maybe square both sides. I've got p minus pi squared is 1.96 squared times then pi times 1 minus pi all over n. And now I guess to solve for n, I would just sort of put n over on the left-hand side. N should be equal to 1.96 squared times pi times 1 minus pi, okay, over p minus pi squared. Okay, so I could tell you the sample size you might want. Okay. But I'm spotting this is something that's quadratic in pi. Okay, yeah, literally, if I were to do the work a little bit, I could note that this denominator term is uncomfortable, and I'll just say it's a quadratic in quadratic form. And so if we use that quadratic equation, remember a times pi squared plus b times pi plus c is 0. Okay, I could put it into that form, and I'm going to, from that, derive n should equal, okay, x, the number of actual successes. Okay, okay, so let's remember p was x over n. Okay, I could write that as x plus 1.96 over n plus 1.96 squared. Okay. Okay, so I'm going to go with x plus 1.96 over n plus 1.96 squared. And I'm skipping some algebra steps here. Are you okay with me skipping algebraic steps? I'm not looking any of your faces here, or I'm not even seeing like the video of y'all. Let's look. Are any of you saying, hey, I want to do the algebra right now? Chase, I don't know how to interpret that. Are you saying you want the algebra, or you say you're good to assume that reading the book will give you what you need? Okay, cool. I appreciate the clarification. So I'm saying the sample size you want to use is going to be x plus 1.96. I'm sorry. I apologize. No. That's not the sample size. I'm going to tell you what n should equal. Okay. No. I'm actually sort of trying something different. I apologize. We're not finding n here. That was a different problem. I mistakenly said that. So if we plug in for p x over n, if I want to plug that in, okay, we can simplify back down to p tilde. Okay, I could write it as x plus 1.96 over n plus 1.96 squared. Okay, I'm going to call that p tilde. That's another estimator. P tilde estimates pi. It's a different way of estimating pi, and p tilde, you could write it as approximately n, or x, the number of hits you have, the number of heads that you have, plus 2 over n plus 4. Okay, so again, solving for pi, you end up with you could bracket pi with this approach, not bracket it. You can tell me that pi is that, and so we're going to let our estimate of pi be x plus 2 over n plus 4. And I'm going to say now we have a confidence interval based on our new estimator pi, or p tilde. I'm sorry, p tilde. So let's write out what that new estimator p tilde is with our margin of error. And I took a picture of that so we can work back if need be. So p tilde, your new estimator, is just n, or no, sorry, the number of successes plus 2 over n, the number of trials plus 4. And I would say my confidence interval, so CI, for the unknown value pi is p tilde, that's my estimate, plus or minus 1.96 times then the root of p tilde times 1 minus p tilde all over n plus 4. And that maybe looks a little bit odd, but that's indeed the way we're going to choose to do this. So maybe that was bothering me. Let's make it not so long, extra long. Don't need it. Okay, so there is my method. And so some of you are thinking, okay, that's a little bit odd, dude. But the nice thing is this approach works even for a small sample size an n of less than large. Okay, we started down the path saying, what if you have a large sample size? We did a little bit of work with the normal curve in simulation studies starting in the 80s, and then in the 90s, pretty much everyone was convinced by then that this method called the Agresti-Cool method for estimating an unknown population proportion. This one is biased, but it does have about a 95% coverage rate, even with small sample sizes. So I could use this with a small sample size. And so an example I like to give is from the show Iron Chef, the original Japanese series, which is better than the whatever the hell they have on Food Network today. But there's one chef who will just say his name is Morimoto, and I may be remembering this incorrectly, but if I remember, he sort of specialized in seafood. Okay, and in a total of n equals 5 episodes, where he battled a contestant, we had X equal to 4 wins. So he had 4 wins in then the 5 trials. Okay, so the question I saw in chat is, why is the denominator n plus 4? The reason boils down to if you have from the page past, if you try to solve for that unknown value pi from that quadratic form of the equation, you end up with a value for pi that looks like that. And so we're just going to, looks like that. And so we're going to use that as our estimator. Okay, so n plus 4. And so sometimes we say this method is, well, the add 2 successes and 2 failures method. Okay, it's almost as though we're going to flip the coin 5 times and say, well, we'll pretend that we had 2 extra heads and 2 extra tails. So let's pretend we had 9 flips. Like we're pretending the Chef Morimoto, we've got 5 trials, okay, wins 4 of the events. And so my P tilde is just X plus 2, okay, over N plus 5. In this case, it's going to be 4 plus 2, or 6 over n plus 5, 9 2/3. Okay, so I'm estimating he's going to win 2/3 of these chef testant battles because he's relatively good. He should be winning about 2/3 of the time. But the sample rate, remember just X over N, that 80%, 0.8. So literally the guy won 80% of the time, but I'm saying, I'm going to say about 2/3. And I'm going to add a margin of error to that 2/3. And with my procedure, which is use this for P and this as the margin of error, we will actually capture the true value, the unknown value pi, about 95% of the time. So let's go ahead and finish that off. My method is 2/3 or 0.67 plus or minus 1.96 times the root of 0.67 times 1 minus 0.67 all over n plus 4. So that's 9. We end up with 67% plus or minus 31%. Okay, so we're 95% sure the actual rate of winning for this Morimoto guy will be in the range of 36 to 98% of the time. That's a really wide range of values. Wouldn't you want a smaller margin of error than plus or minus 31%? You probably would. So we can go ahead and use our trick. Okay, and the trick is, let's take our overall margin of error. Okay, let's set that capped at B. So B, we want B to be an upper bound on the margin of error. So B should be greater than or equal to 1.96 times the root of P tilde times 1 minus P tilde all over N. And I can now solve for N. The N I'm going to want to choose would be at least 1.96 over that target margin of error, B, that I want to bound things at. Square that times P tilde times 1 minus P tilde minus 4. Okay, so algebra just will result in this equation. And then, like before, with our standard deviation not being known, we had to plug in a sample standard deviation. We need on the right-hand side to plug in a p tilde value to tell me what is the sample size I'm going to need to estimate pi with p tilde. I have to know a p tilde on the right-hand side so I can determine the sample size, so I can even calculate p tilde in the first place. So there are 3 approaches to the value for p tilde that you're going to want to use. And actually, there's more than 3, but I'm going to emphasize, well, let's go with 4, okay? 4 possibilities for p tilde. And starting at the top, I'm going to go with, what if you have no idea at all what value pi is? No idea. And you want to guarantee that your bound b on your margin of error is hit. Use a p tilde of exactly 1/2. So that's a guarantee. It will get you your target margin of error, or even smaller. So your n should be set that way. Just plug in 1/2 for p tilde. Another approach, second approach, maybe a new color. Let's go blue. You can use prior data. Prior data. From the population you're sampling from. Yeah, literally. I don't have already a sample, perhaps, but if I do have a sample, I could get p tilde from that prior data set and use that p tilde as a way of, well, putting in the input on the right-hand side. Third approach would be similar data. So here's an example. So Cal Poly, as was mentioned on the midterm, has the desire to find out what fraction of students actually are willing to get in a car that's is being driven by someone where the student who voluntarily gets in the car, that person who's driving actually has been consuming alcohol. So that's like a student safety thing. No comment on the driver. I'm just commenting only on the wisdom of getting in a car when someone has been driving. Cal Poly would like to know the number. What fraction of y'all have done that? Okay. And indeed, we don't have a past sample of Cal Poly students where this was done. But you know what? At UCSB and at UC Davis, we do have samples because they already asked this question. And I'm thinking, let's just use the data from 2 comparable institutions, because most of you all applied to one of those 2 schools and got into it and then chose to come here instead. And so you're in many ways sort of like the students that apply to UCSB and Davis, okay? Those are the 2 campuses that have the highest overlap in terms of students who apply to Cal Poly and some other school, okay? So let's take data from comparable or similar students and plug in the p tilde from those 2 campuses, okay? And that's a good idea, because then it will allow us to calculate the sample size n that we need. Another approach is to, again, use a wise approximate guess, or a wild ass guess, either way. If you don't like the guarantee approach and using 1/2, because you think your value for p is like 0.9 or 0.8, or maybe like at the bottom end 0.03 or 0.07, somewhere in that tiny range. Okay, just take your guess and use that instead. It will ultimately give you the sample size recommendation that we would recommend you use. Any questions about calculating that sample size? Oh, sorry. That's a class from yesterday, and that's not what you needed to see. Okay, good. So any questions about that method of calculating a sample size for a Poisson rate or confidence interval? Like literally an estimate with a margin of error. The best estimate is biased because it gives us the target level of confidence we hit about 95% of the time with that approach. So we like that approach. We want to use it. Okay. Okay, so let's get back into yesterday's question and tackle the small sample size approach. Yesterday's method with this Z equation, we just said, you know what, large sample, approximately normal, all good. You know, what if you're sampling from a population that is normal in shape? Okay, so I'm trying to draw that normal shape, and you want to know sigma. Okay, and you are not knowing, you want to know mu, but we don't know sigma or mu. We know neither of the population characteristics, the normal. And like before, we said we're going to take a sample of size n, okay, from that population. So n is the sample size. We get x1, x2, all the way up through xn. Okay, those are the data values. X bar is the average, and S is the standard deviation. The method we have for our confidence interval from yesterday is the CI approach. Okay, was X bar. Use your sample mean to estimate the unknown population mean, because that's unbiased. Plus or minus. Okay, and what we had is Z alpha over 2 for and 100 times 1 minus alpha percent confidence interval. So yeah, usually we use 95% confidence. So Z alpha over 2 is like 1.96. And we had times S over the root of N. But if my sample size N was not big, I'm in this awkward spot where I'm saying, let's go ahead and use S, a sample standard deviation, which might very imprecisely tell me what I should use for sigma. S might be far off from the truth. Okay. And so there's a little bit of interesting reading, or you could look up a guy named Gossett, Gossett. He worked at the Guinness Brewing Factory and did this mathematical work. There's these two-dimensional thing, and he integrated over one of the dimensions and came up with what we're going to tell you today. And what we're going to tell you today is, no. Don't use Z. Use instead this other curve that we will term the T curve. X bar plus or minus T alpha over 2 degrees of free. Alpha over 2 is the upper tail area, but it's going to be characterized by what we will term degrees of freedom as well. Okay, and we're going to multiply that. Let me move this down so that way it's clearly lower, because it's in the subscript right next to the alpha over 2, df. And then we're going to multiply that by S over the root of N. And in past classes, I've termed S over root N as the standard error of X bar. It tells us how close X bar is likely to be to mu. But let's focus on this T value instead of the Z value. T, the value, has two subscripts that sort of define it. One is that upper tail area, and that we've got. That's easy. This second degrees of freedom is, well, I'll just say it's related to the number of data points that you have, okay? And degrees of freedom for this approach, degrees of freedom, is just the number of data points minus 1. You can see that if you have a lot of data, conceptually, you can see that if you have a lot of data values, your S is going to quite nicely approximate sigma. But if the number of data values that you have, N, is small, like 5 data points, S might be quite a bit larger or quite a bit smaller than the actual value sigma I'd love to put in this place. And so we're averaging over all possible S values, or better, S squared values. And here is the approach we should be using. Use this other value, this other curve instead. So let me show you how to find the T value. And there is a T table. Our book also walks you through. Maybe I'll Move this over here off to the side, take a little screenshot real quick, then move it back and remove the clutter. And we'll focus on how to get JMP to give you your T value with this distribution and probability calculator. Okay. One, the book walks you through how to use the T table. It's in the back of the book. I put a link to it on Canvas. You could download that and print that out to your heart's content. But most of you in past class sessions have said, yeah, that distribution calculator, I'm cool with it. I'll go ahead and use it. Okay. So what distribution? Well, let's just use the next one down. The first few are sorted in terms of how likely you are to need to use the tool. T is the commonly used. Okay. And you can spot degrees of freedom is a number that you have to plug in. And I'm going to run with 10 for now, as though our sample size was 11, which gives us 10 degrees of freedom. Again, n, the number of data points, minus 1 is the degrees of freedom I'd use for this approach. And I want a central probability of what? Well, 0.95. I'm going to plug in 0.95, and it tells you my T value that I would use is like 2.28. I'm sorry, 2.2281 or 2.228. If you round way too much, you'd say 2.23. But I'm going to say the T value is quick. 95% middle area. I'm home free. What if I have only, say, 2 degrees of freedom? We're seeing my T value is going to be, let's reset that distribution. I'm going to see that central area of, I'm sorry, input a probability and then calculate an area. That central probability of 0.95, 0.95, that central area gives me a T value of 2.2. Okay, so 2 degrees of freedom. Good. Okay, so 2 degrees of freedom, and I now get to choose the probability and 0.95, and it gives me my T value for 0.95. Okay, 2 degrees of freedom. That's that. Ignore this graph upstairs. It says your T value that you ought to use is 4.3. What if your T corresponds to 25 data points and minus 1 would be 24? I'll put in 24 values here. My T distribution with 24 degrees of freedom. I would plug in central area 0.95. I'd use 2.06. What if I had to say 100 degrees of freedom? Boom. I would have a T value of 1.9840. And so I'm spotting for degrees of freedom that are anything other than tiny. Okay, my value for T is going to be about 2. If I want 95% confidence, my T value should be about 2. So that's why earlier, like yesterday, I just said, go ahead and use, just go ahead and use a 2. And then we were a little precise yesterday and said, but no, we'll look it up at the normal curve and we'll use 1.96. Here's what most statisticians I know do. We're going to use software to get the right answer. But if we're doing it in our head, you're going to say, oh, 95% confidence in the degrees of freedom, the number of data points approximately is not tiny. I'll just use 2. Up and down 2 standard errors will be about the right way to go. Let's try and justify that one more time. But from the point of view of the student taking a test, I know you have the opportunity to get from this probability distribution calculator T. You could plug in degrees of freedom. You could say, yeah, I want 95%. But that walking through that, like firing up the software and doing all, it might take like a full-on minute. And if you have not that much time, not even a minute to go on your exam, and on the final exam, it's going to be like twice as many questions. Okay. But you'll have 3 times as much time to do it. So you shouldn't run out of time. But if you feel pressure, just use a T of 2. Because as long as the degrees of freedom isn't tiny, 2 will get you an approximate answer. You're going to be getting in the ballpark. You'll be doing it the right way. Okay. And statisticians, we even noticed that this method works with the normal population and a small sample size, it will also work better than the Z approach with a large sample from a normal population. So we pretty much always use this T distribution unless we're convinced we have a small sample from a noticeably skewed or perhaps bimodal distribution. Our method here, this T-based confidence interval, works really nicely. Okay, so let's get after this with our catfish earlier, and I want to know perhaps how much larger the catfish are from one species than another. And so our catfish data set over here, boom. I've got blue catfish and channel catfish. Actually, hold on, that's all the species. Maybe I have it just with 2 species. Darn it, I don't have all the species, but notice that I have blue catfish deselected. We did that yesterday. If I wanted to focus on just blue catfish, okay, I'm home free with my method. Okay, so I'm gonna say let's analyze. Let's analyze the distribution of the lengths of my blue catfish. Again, I don't like that vertical orientation. I like it horizontal. So I'm going to look at it this way. And I'm 95% sure that the average length is in the 340 to 354 range. You're saying, but hold on, dude, this is not normal. And I'm saying, well, but I got a large sample size. My sample size being 2,600, that's certainly more than 30. I definitely need, I definitely need to feel some comfort. I definitely can use this method. The T distribution is about the same as the normal curve if the degrees of freedom is big. And in this case, we have 2643 degrees of freedom. That's almost darn near exactly the normal curve. I'm home free to use the method. So when we said yesterday, oh, let's compare our Z-based answer to what the software gives us, we were happy because we used the method the right way. Okay, so one more thing that I would like to do, and that is, what if we're trying to compare 2 populations, and let's call them population 1 and population 2. And I'm going to phrase this in the context of a small sample approach, but we'll still use it even if, we're going to use this even if our sample is large in size. But we need to, if we have a small sample, we need to have a normal shape distribution. So the method works with normal shaped curves from each of the 2 populations. And our 2 populations will have in each one a mean. So mu1 and mu2 from population 1 and 2. I've got sigma 1 and sigma 2 from that second population. 2 means, 2 possibly differing standard deviations. Just a quick tech note here. Our book walks you through a whole thing called a pooled t-test, which says, what if you are willing to assume that sigma 1 and sigma 2 are actually the same? And I'm saying, I know of no one who uses that method that our book starts you with. Okay. Our book says, if you have these 2 identical population standard deviations, go ahead and use this method that is only slightly narrower in terms of the margin of error than the one this method is going to be using. So the pooled standard deviation approach, I'm not recommending it. I know of no statisticians that use it unless the person they're working with insists that really sigma 1 and sigma 2 are the same. And if the 2 sample sizes are the same as well. So we've got normality or a large N here, and my confidence interval, okay, my 100 times 1 minus alpha % confidence interval for, I'm gonna write mu1 minus mu2. Yeah, literally, I want to know how much higher the one group's average is than the other. Mu1 minus mu2 is a number I would love to estimate. That is my theta, if you will. My theta hat, my estimate of mu1 minus mu2 is x bar 1 minus x bar 2. Literally, I'm going to find the difference of the sample means, because that is an unbiased way of estimating the difference of the population means. We've got two samples that each separately estimate the two populations. So to estimate the difference of the population means, let's just use the difference of the sample means. But my confidence interval, I want to go ahead and put a margin of error on that. So plus or minus. We'll go with green here. Plus or minus what? Well, we're going to have two parts to it. One is T alpha over 2. And then I'm going to, again, say degrees of freedom, but we'll give you a different approach to degrees of freedom. And then we're going to multiply that by the standard error for the difference of the sample means, or if you will, S1 squared over N1 plus S2 squared over N2. And so the problems where you're going to have to do it will typically give you two separate sample means, two separate sample sizes, two separate sample standard deviations. So you're going to have all of that information ready at your fingertips, okay? So you're in good shape there. Okay? Let's focus on one last thing. And what should I use for degrees of freedom? df equals what? Okay, the approach for degrees of freedom is going to be based on whether you've got a computer in front of you, whether you're willing to assume the almost certainly incorrect sigma 1 equals sigma 2 thing that gets you to your pooled method, okay? You could say degrees of freedom is equal to n1 plus n1 n2 minus 2. Don't use that method. That would be corresponding to the pooled approach. Don't use it, okay? Another approach that you could use if you don't have the software in front of you and you then want to still know degrees of freedom to use, if you have to use an approximation by hand, I would say use the smaller of the two sample sizes and subtract 1 from that. Yeah, literally use degrees of freedom for the smaller of the two samples. And this will give you a conservative approach to degrees of freedom. Your degrees of freedom will be a little smaller, and thus your confidence interval will be a little wider than the one I'm going to suggest to you that you probably ought to be using. And that is the auto magic approach. And let's go with purple, because purple will stand out, okay? I'm just going to degrees of freedom from an equation, page 327, or software. Pretty much every single software package on the planet where you say, I want to use a T procedure, it will say, oh, I know page 327's equation. That's the one I'm going to use. That's the approach I'm going to use. So let me show you in the context of the catfish, how you could get the software to do what you want it to do. Again, we've got our catfish varieties, and I want to compare the lengths of blue catfish and channel catfish. But the channel catfish have been eliminated from my analysis, like the flathead and the white catfish. But if I select one of the channel catfish cells, and then right click there and say, yeah, pick up all of the channel catfish. Notice how they're all, the red slashy and the face mask thing. Do not include in the calculations at all, and do not show any of these data points. If I right click and say, you know what, hide and exclude, no. Let's just toggle that. And it gets rid of the hide and the exclude. We're going to now include blue catfish and channel catfish both in our analysis. So the analysis, the way I would do this now, in the lab, which will appear later today, we'll walk you through, analyze fit y by x. Okay. Yeah, literally I want to know about the lengths. My response variable's length. How much does the length differ between my two species? Well, species is the factor or the X variable for my comparison, how much different is the length on average between the two species? That's really what I'm tackling. I click OK. And I get a graph. Pretty much GMP always likes to create graphs first thing. And the graph says the blue catfish over here and the channel catfish over here. If I say, you know what, turn on my T-based procedure, it's called a T-test, but that's next chapter, so we'll call it a T-based procedure. Turn it on. I'm going to have the channel catfish minus the blue catfish. Okay, channel catfish length minus the blue catfish length is on average negative 26 millimeters. These guys are shorter than the other by 26. I could even show you graphically how that is under our graph display options. I could show you literally the lines where the averages are. The one group is 26 millimeters higher than the other group. Blue catfish, 26 millimeters higher on average. But notice the CL, the confidence levels, upper and lower. I'm 95% sure that these channel catfish that are smaller are 16 to 36 millimeters smaller on average. So literally, we're comparing the two population means. Literally, we're saying, here's your estimate of the two population means differences, 26 millimeters, with a margin of error of plus or minus, well, like 10 units, 10 millimeters, a centimeter. So the one group is 26 millimeters smaller than the other group, but I'm 95% sure in general out there in the population, it's 16 to 36 millimeters shorter in length. Okay, so the confidence limits you get for free in addition to your difference. You even have the standard error for the difference, the root of S1 squared over N1 plus S2 squared over N2. The key part of the lab, though, that will be online as soon as I'm done with chatting with students in office hours, is can you get the procedure to get done, and can you maybe adjust the confidence levels to get the target level of confidence? Can you even solve for the sample size that you want from each group to be able to get the target level of confidence? But that's a good place to stop because we hit the 1 o'clock. And so I'm going to stop sharing screen, and you all may have a question before I stop the recording. But if you don't, well, I'm going to stop that recording. Any questions, though? Okay, I stopped the recording.